This lecture looks at resistors in circuits. There are two basic ways of arranging resistors in a circuit: series and parallel. In series, you put one resistor after another. The longer path increases the resistance. The charge has a greater distance to travel through that has resistance. What is the equivalent resistance if you measured from point A to point B of these two resistors? Or in other words, if we put a box there and measured from point A to point B, what would be the resistance inside the box? Well, let's call the first resistor R1 and the second resistor R2, and both of them will have the same current I going through them. And let's also label the voltage at point A to be VA, at B, VB, and at a midpoint between the two resistors, V mid. Then we can use Ohm's law on the first resistor so that VA minus V mid is equal to current through that resistor times R1. Similarly, for the second resistor, we have V mid minus VB is equal to the current times R2. If we add these two equations, the V mids cancel, leaving VA minus VB times the current times R1 plus R2, and this R1 plus R2 is the equivalent resistance. If you have many resistors in series, the equivalent resistance, Req, is just the sum of all the resistors, R1 plus R2 and so on. Resistors in parallel have the resistors put so that there are two paths to the circuit or more. Connecting resistors in parallel decreases the resistance because there is an extra path. What is the equivalent resistance in this case? The key is that the voltage on the left side of both resistors is VA, and the voltage on both sides on the right side of both resistors is VB. So that if we look at the upper branch, VA minus VB is equal to I1 times R1. So that's just Ohm's law on the upper branch. Solving for I1, we get the current I1 is equal to VA minus VB divided by R1. On the lower branch, we have VA minus VB is equal to the current through the second resistor times the resistance of the second resistor. And solve again for I2, we have VA minus VB divided by R2. Now the total current flowing into this parallel resistance is equal to VA minus VB divided by the equivalent resistance. Or it's also equal to I1 plus I2 from Kirchhoff's first law, because we have I2 flowing in and I1 and I2 flowing out of the entrance. If we take both of these, then we have VA minus VB divided by R equivalent is equal to VA minus VB divided by R1 and VA minus VB divided by R2. And all the VA minus VBs cancel, leaving us with that the inverse of R equivalent is equal to the inverse of R1 plus the inverse of R2. Solving for Req, we have that is equal to the product of R1 and R2 divided by the sum of R1 plus and R2. If there are many resistors in parallel, then 1 over the equivalent resistance is equal to the sum of all the inverses. So that's 1 over R1 plus 1 over R2 plus 1 over R3 and so on. Let's look at some examples. What is the equivalent resistance from A to B for the set of 6 identical resistors shown? There's a set of 2 and a set of 4 parallel resistors. So first let's look at the 2 resistors in parallel. So 1 over R2, which is the equivalent resistance for the 2 in parallel, is equal to 1 over R plus 1 over R. And that's simply equal to R over 2. 4 resistors in parallel is 1 over R4 is equal to 1 over R plus 1 over R plus 1 over R plus 1 over R. And that gives us an R sub 4, which is equal to R divided by 4. the equivalent, since their two sets are in series, they simply add. So R equivalent is just R2 plus R4, which is 3/4 of R. What is the current through each of the resistors in the circuit shown below? We have a voltage driving current through these three resistors. We have an R1, which has an I1 going through it, an R2, which is an I2 going through it, and an R3, which is an I3 going through it. R2 and R3 are in parallel, so our first step is to find the R equivalent of the parallel resistors, and that's just 1 over R equivalent is equal to 1 over R1 from the second resistor, and 1 over R3 from R3. If we go ahead and solve that, we have that Req is R2 times R3 divided by the sum of R2 and R3. We're going to use that a little later, so I'll put a green square around that. The second step is to draw a simpler circuit using this R equivalent. So we replace the parallel resistors with just one resistor, which has the value of Req. And now there's only one current through the whole loop, and that's I1. That is the current that goes through R1. So if we use Kirchhoff's second law on this simpler circuit, we can write down the voltage and voltage drops around this loop. So we have a voltage source minus I1 R1, that drop, minus I1 R equivalent, that drop, equal to 0. And then we can solve for I1, and that's equal to the voltage source, that value, divided by R1 plus R equivalent. And we have our first current. So we're a third of the way done. In our third step, we realize that if we knew VAB in the original circuit, we could use Ohm's law to find I2 and I3. This is the original circuit. But it's hard to find VAB in the original circuit, so if we look at the simpler circuit, we can see that we can get VAB easily, just using Ohm's law on the simpler circuit, because between the voltage VAB is just I1 times R equivalent. We know I1 from above, that's V divided by R1 plus R equivalent, multiplied by the Req, and we have VAB. Then, if we go back to the original circuit, we have the voltage across R2 or R3 is VAB, so we use Ohm's law to find I2 and I3. So VAB is equal to I2 times R2. Solving for the current, we have I2 is equal to VAB divided by R2. And then for the R3, we have VAB is equal to I3 times R3. And solve for the current again, and we have I3 is equal to VAB divided by R3, and we have the third current, and we are finished.